Imagine waking up one morning to find out that everything you thought you knew about the cosmos had politely packed its bags and walked straight out the door. Because if there is one idea that flips the whole space colonization conversation on its head, it is this: Venus. Yes, the same Venus that could flambe a spacecraft faster than a forgotten pizza in the oven might secretly be a better candidate for human colonization than Mars. This is the kind of twist that makes the universe feel like it has a mischievous sense of humor. For decades, Mars has been the poster child for future human settlements, the cool red neighbor everyone treats like the cosmic equivalent of a promising real estate development. People talk about Mars the way realtors talk about up-and-coming areas, ignoring the part where the atmosphere is basically thinner than a politician's apology and temperatures swing like a mood ring during finals week. Meanwhile, Venus has been sitting there in the corner, glowing like a lantern with a temper problem, its reputation so sizzlingly bad that most people assume it is the very last place any sane species would want to visit. Venus is the universal example of where not to go. The surface is a pressure cooker wrapped in a sauna, wrapped in a tantrum, with temperatures capable of melting lead before lunch. It is the kind of place where you would step outside and instantly understand how a grilled cheese feels. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now let's begin. So the fact that anyone, anywhere, would dare suggest Venus might offer some hidden advantages feels a bit like saying the best place to build a beach resort is inside an active volcano. And yet, that is where the story gets interesting, because hidden beneath Venus's fiery personality is a twist that catches even space enthusiasts off guard. The planet that has been cast as the villain in every planetary comparison chart has something Mars does not have, something so surprising that it makes scientists tilt their heads like confused golden retrievers. While Mars has charm, Venus has potential. Not surface potential. Nothing survives down there except crushed hopes and future archaeological mysteries, but potential in a place we rarely talk about, the sky. And this is where the whole conversation suddenly pivots from absolutely not to wait, hold on a moment. Above the surface of Venus lies an atmospheric layer that is astonishingly more Earth-like than anything Mars can offer. It is a region suspended high above the planet where the temperature becomes surprisingly comfortable. The pressure becomes almost familiar, and the dangers start shifting from instant death to manageable nuisance. That alone is enough to make you wonder if humanity has been judging this planet a little too quickly. It is the equivalent of discovering that the creepy haunted house at the end of the street actually has a gorgeous, fully furnished penthouse on the upper floor, complete with stable climate control and lighting from your own personal star. And yet nobody ever told us, because we all got distracted by the monstrous basement. Space exploration often trains our eyes downward, toward surfaces, toward land we can stand on. But Venus invites us to look up, to consider that maybe the best place to live on another world is not on the ground at all. Maybe it is among the clouds, drifting in an environment that feels shockingly familiar compared to the Martian alternative. And the best part, this twist does not rely on science fiction. The idea is grounded in real atmospheric measurements, real data, and real planetary comparisons that make the whole debate suddenly feel far more open than the classic "Mars is our future" narrative. It reshapes the stakes. Instead of asking, which planet is less terrible than the other, we start asking, which world can humans actually adapt to in creative, unexpected ways? Because if Venus, the planet famous for frying spacecraft like battered shrimp, has a hidden zone in its atmosphere where humans could theoretically float, breathe comfortable pressure, and bask in generous sunlight, then the universe is telling us something bold. Maybe our imagination has been too narrow. That is the spark that ignites this entire journey, the tension between expectation and possibility, the thrill of overturning an old scientific assumption, the sheer joy of discovering that the cosmic underdog may not be the one we thought it was. This chapter is where we peel back the first layer, where the story begins its slow turn into the surprising, the speculative, and the oddly hopeful. Because whether or not Venus truly stands a chance against Mars, it deserves a fair trial. And to give it that trial, we must be willing to step away from the planetary stereotypes we have been repeating for decades. We must let curiosity lead the way. So as we start this journey, keep that spark alive. The idea that the universe still has surprises, still hides secret opportunities in places we least expect. If Venus can go from cosmic cautionary tale to potential future home, then who knows what else we have misunderstood? And if we dare to look beyond the first impression, we might discover that the hottest planet in the solar system is not just a furnace of doom after all, but a challenge begging us to imagine something bolder. Mars has worked its way into the human imagination so thoroughly that it might as well start charging rent. It is the planet that has been starring in our dream of a cosmic second home ever since telescopes became powerful enough to turn its fuzzy red smudge into an actual world with deserts, canyons, and the faint promise that something interesting might have happened there once upon a time. Pop culture feeds that dream with enthusiasm. Mars appears in movies, novels, video games, and even cereal box level space facts, always framed as the place where humans could go next. If Earth ever needs a backup drive, Mars gets penciled into the plan with big, optimistic handwriting. It is like the reliable cousin who shows up to every family gathering, quiet, cold, but dependable. Even the way we talk about Mars has this undertone of expectation. What will we grow there? How will we survive there? What color will our Martian farm boots be? Mars feels familiar, almost friendly, even though the planet itself is not exactly rolling out a welcome mat. Contrast that with Venus, which occupies the opposite end of the cosmic personality chart. Venus has a reputation that could only be described as antagonistic. It is the world teachers bring up in class when they want to shock students into remembering what runaway greenhouse effects look like. Whenever Venus gets mentioned, it is usually followed by phrases like crushing pressure, scorching heat, or an atmosphere that wants you to fail. Venus is treated as the planet equivalent of that one neighbor whose porch lights flicker in a suspiciously horror movie way. Nobody daydreams about building the first settlement there. Nobody doodles Venusian colonies in their school notebooks. It is a world dismissed so quickly that you can almost hear the door slam shut after its name is spoken. If Mars is the cosmic backup plan, Venus is the cosmic don't even think about it. But reputations, especially planetary ones, have a strange way of sticking long after new information comes along. Mars has been basking in the warm glow of human curiosity for centuries, even though we have learned that its environment is more challenging than its early reputation suggested. Venus, meanwhile, never recovered from its early introduction to science as a hostile inferno. Once a planet earns the title of solar system supervillain, it becomes hard to see anything else. And yet, when we peel away the dramatic headlines and stop imagining Venus as a metal-melting bully, we find a world that is misunderstood in the most fascinating way. The reputation problem begins with our expectations. When astronomers first studied Venus in detail, they expected something Earth-like. After all, Venus is almost Earth's size, Earth's mass, and Earth's next-door neighbor. But instead of beaches and sunsets, they found a planet wrapped in thick clouds, hiding a surface that behaves like an oven with performance anxiety. Those early discoveries made Venus sound like a warning label rather than a destination. Meanwhile, Mars, although barren and icy, looked honest about its struggles. It did not hide behind clouds. You could see its surface. You could map it. You could imagine walking on it without immediately evaporating. Mars seemed approachable, like a fixer-upper house with good bones. Venus seemed like someone had taken that fixer-upper, set it on fire, and then politely left the room. This created a strange bias in how we think about these two worlds. Mars has had decades of public relations brilliance, even without trying. Every rover that lands there becomes a celebrity. Every photo from its surface gets shared like a cosmic postcard. It has become the pet project of visionaries who design habitats, greenhouses, suits, and entire city layouts for a place where no human has ever set foot. The enthusiasm is contagious. When people imagine colonization, they imagine Mars by default. They imagine red dust under their feet, not sulfuric acid clouds drifting around them. Venus does not get that kind of enthusiasm. It barely gets a fraction of it. If Mars is the planet we treat like an inspirational poster, Venus is the planet we treat like a cautionary PowerPoint slide. But this is where perception cracks away from reality. Venus deserves a second look precisely because our understanding of it has been shaped by assumptions that do not tell the full story. Its surface conditions overshadow everything else about it, like a bad headline that drowns out the nuance of an article no one bothers to read. When we re-examine Venus without the dramatic flair, what we see is a planet with an identity far more complex than its molten reputation. It is a world that mirrors Earth in unexpected ways, a world whose atmosphere has layers that behave differently from its surface, a world that does not fit neatly into the villain role we assigned it. Reputations are powerful, but realities are often far stranger and more hopeful than we expect. Mars may have captured the spotlight, but Venus has been lurking behind the curtains with a story that challenges everything we assume about where humans could someday thrive. By questioning these long-held perceptions, we open the door to possibilities we never thought to explore. And sometimes, all it takes is a shift in perspective to turn a cosmic villain into a surprising contender for humanity's next great adventure. If planets were auditioning to play Earth's understudy, Venus would be the one standing on stage with the same height, the same build, and surprisingly similar posture. It is almost uncanny. Venus is just a bit smaller than Earth, just a bit lighter, and yet dense enough that it feels like it is trying to imitate our home world with near-perfect dedication. This resemblance is not subtle. It is as though Venus peeked at Earth's cosmic measurements and said, "I can match that. Give me a moment." Before you even get to the atmosphere or chemistry or anything that tries to cook you alive, the physical structure of Venus itself is the closest twin we have in the entire solar system. When you strip away all the drama, Venus is built on the same architectural blueprint that Earth follows. Gravity is where this resemblance becomes especially important because human bodies are picky. We evolved under Earth's steady pull, the one force we never stop feeling, even when we think we are relaxing. The gravity of Earth shapes how our muscles grow, how our bones renew themselves, how our fluids circulate, and even how our sense of orientation works. Take humans away from that familiar pull, and the body starts filing complaints. In microgravity, bones lose density, muscles shrink, and the entire circulatory system behaves like it has forgotten the assignment. Even slightly lower gravity can cause long-term issues, which is why Mars raises concerns. Mars's gravity is barely more than a third of Earth's. Live there long enough, and your body might try to remodel itself into something better suited for a world where things feel strangely lightweight. That sounds fun, until you realize that the next time you visit Earth, walking upstairs could feel like climbing a mountain while wearing a backpack filled with bricks and questionable life choices. Venus, however, does not fall into that trap. Its gravity is only a little lower than Earth's, close enough that your bones and muscles would not feel abandoned by physics. The difference is so small that daily life would not require the kind of full-time physiotherapy that long-term living on Mars might demand. The body loves consistency, and Venus offers a gravitational environment that is familiar enough that our biological systems would not need to rewrite their instruction manuals. This is not just about comfort. It is about long-term sustainability. A colony can survive only if the humans in it remain healthy without needing to wear robotic exoskeletons just to keep their bones motivated. Beyond gravity, the size of Venus carries its own advantages. A planet's radius determines how curved its horizon feels, how land spreads out, and how your sense of space works. Mars, being smaller, has a tighter curvature. You can see the effect in rover photos. The horizon looks close, as if the world ends just a short distance away. On Venus, the horizon would feel far more Earth-like. Even if habitats floated high above the surface, the perception of scale would resemble home. Humans are surprisingly sensitive to the geometry of the world beneath them. We are used to the subtle hugeness of Earth's shape. Venus, with its nearly equal size, taps into that instinct. Density adds another layer to this physical familiarity. Venus is dense in the same way Earth is dense, made of rock and metal, with a structure that feels solid and grounded. A world's density influences how deeply its gravity digs into the bones of the planet, setting the stage for how it rotates, how it holds heat, and how it shifts over eons. Even though Venus rotates slowly, slow enough that its day is longer than its year, the structure of the planet itself is remarkably stable. This stability creates a physical presence that feels dependable, the kind of cosmic sturdiness you would look for if you were planning to build anything long-term. Mars, by contrast, is like a lighter version of a planet, puffed up with empty volume. It has less mass pulling everything inward, which means less gravitational glue holding its surface environment together. That difference subtly shapes the psychological feeling of living in each place. Standing on something Earth-sized, whether on the ground or floating above it, gives a sense of belonging that smaller worlds struggle to offer. These similarities matter more than we often admit, because colonizing another planet is not just about machinery and engineering. It is about biology and psychology. It is about creating a place where humans can thrive without slowly unraveling under unfamiliar physical conditions. Mars, with its weak gravity, invites a future where long-term settlers might become genetically distinct from Earth humans, shaped by the gentle pull of a smaller world. Venus, with its nearly Earth-like size and gravity, offers a way to keep humanity's physical blueprint intact, to maintain the close relationship between body and environment we evolved with. And the best part is that these traits are intrinsic. They do not require terraforming or technology or artificial compensation. They are simply built into the planet, waiting for us to notice. While the dramatic challenges of Venus tend to dominate the conversation, its structural similarities to Earth quietly sit in the background, offering an unexpected sense of familiarity. In a universe full of worlds that are too small, too light, too thin, or too alien, Venus stands apart as the one place that mirrors the physical feel of home, an unlikely twin beneath its turbulent skies, reminding us that even the most misunderstood planets can hold surprising advantages. If Venus's surface is the cosmic equivalent of sticking your head inside an industrial oven set to incinerate, then its atmosphere is a layered story with plot twists that even seasoned scientists did not see coming. To understand why Venus becomes interesting again as you climb upward, you have to picture the atmosphere not as a single hostile blanket, but as a towering stack of wildly different environments, each layer shaped by physics, pressure, and heat in ways that feel almost theatrical. At the bottom, the planet is furious and unforgiving. But higher up, much higher up, Venus softens into something so unexpectedly pleasant that it almost feels like the punchline to a cosmic joke. The same planet that can melt metal on the ground turns into a surprisingly temperate refuge when you rise far above the chaos. Near the surface, Venus behaves like it is trying to win some sort of award for most dramatic temperature performance. The heat is intense enough to roast spacecraft, punish metal alloys, and make rocks glow with a heat you can practically imagine radiating through your boots. It is the kind of environment where you could throw a frying pan into the air and it would land fully cooked. But the reason for this unbearable environment becomes clear once you consider the sheer weight of Venus's atmosphere. The pressure is immense, squeezing heat downward, trapping energy, and refusing to let anything cool off. This is where the planet gets its fiery reputation, a reputation so loud and overwhelming that most people never bother to ask what happens farther up. The truth is, Venus's atmosphere behaves a bit like a pressure cooker on the counter and a cozy living room at the top of the ceiling. The deeper you go, the more trapped heat you find. But as you go up, layer by layer, the pressure drops off and the temperature follows suit. Climbing through Venus's atmosphere is like ascending an incredibly large mountain. Except instead of reaching snowy peaks, you reach a world that suddenly feels almost Earth-like. The climb from the surface to these upper layers would take you through a gradient so dramatic that it feels like slipping between different chapters in a planetary novel. By the time you reach roughly 50 kilometers above the surface, the most astonishing shift occurs. The temperature stabilizes into a range that a human being could recognize as comfortable. Not chilly, not scorching, just comfortably warm. Depending on the exact altitude, it can feel like a late summer afternoon, the kind where you might consider opening a window for a breeze. This region, tucked safely above the worst heat, and below the cold thinness of the upper atmosphere, is known as the habitable cloud layer. And despite its dramatic name, it is not science fiction. It is a real, measurable zone where the environment, at least in terms of temperature and pressure, lands within the range of human tolerance. This is the moment when Venus stops being a villain and starts quietly raising its hand as a contender. Because the habitable cloud layer is not just mildly warm, it is stable. Planetary atmospheres are shaped by physics that do not care about our comfort. Yet somehow Venus has ended up with a zone that seems remarkably kind to human physiology. Temperatures hover around what you might find in a heated indoor pool area. The pressure matches what you would experience while standing on the beach. It is such a stark contrast to the inferno below that it feels like discovering a hidden room in a house you thought you knew and finding it furnished and inviting. There is a certain elegance to how this layer forms. Venus's thick atmosphere traps enormous amounts of heat near the surface, but heat does not behave the same way at every altitude. As gas expands with lower pressure, it cools. The upper layers of Venus's atmosphere, despite being made of the same materials as the lower ones, follow this rule faithfully. The result is a temperature curve that falls dramatically until it passes through a sweet spot one single band where everything feels balanced. These temperature differences do more than just reshape our expectations. They redefine how we imagine living near Venus at all. No one is planning to build anything on the surface unless humans suddenly evolve into titanium-based organisms who enjoy baking from the outside in. But above the surface, in this stable band of comfort, the possibility of floating habitats becomes more than a thought experiment. The environment there is not merely survivable. It is surprisingly welcoming, like a celestial balcony overlooking a world that is far less inviting below. The habitable cloud layer introduces an entirely different way of imagining planetary colonization. Instead of planting our feet on alien soil, we imagine drifting gently above a hostile landscape, supported by physics rather than fantasy. And while temperature is only one factor in this vision, it is a crucial one. A world where the atmosphere offers a natural safe zone becomes a world worth reconsidering. Venus, for all its fiery bluster and surface-level rage, contains this gentle upper refuge that defies expectations at every turn. It is as if Venus hides a secret personality, one that whispers above the noise of the headlines. Yes, the surface is catastrophic, but the skies, high above the pressure and heat, form a place that sits shockingly close to human comfort. This is the contradiction that makes Venus mesmerizing. A planet so extreme and unforgiving also harbors a layer that fits our biological needs with uncanny precision. It challenges the way we think about worlds, about habitability, and about what dangerous really means. Because sometimes the key to survival is not to dig deeper, but to rise higher, far above the furnace, where Venus reveals its gentler side. Stepping onto the surface of Venus would feel less like exploring an alien world and more like volunteering for the world's most dangerous pressure experiment. The atmosphere down there does not ease you in politely. It presses down with the force of 1,000 Earth oceans stacked on your shoulders. The kind of pressure that would flatten a submarine before it had time to protest. It is a world where gas behaves like an unstoppable weight, where the air itself becomes a physical presence strong enough to crush spacecraft into something resembling abstract art. If you could walk onto the surface, which you cannot unless your long-term goals involve impersonating a canned tomato, you would experience a pressure so extreme that it makes the deepest point of Earth's ocean look almost playful. But pressure, like temperature, is a storyteller. It shifts dramatically with altitude, revealing new chapters of the atmosphere that feel nothing like the one before it. Venus's atmosphere is deep, layered, and structured in a way that turns the climb from the surface into a journey from catastrophic compression to startling comfort. As you rise, the oppressive weight drops quickly. Gases expand, the atmosphere thins, and the crushing force begins to ease, transforming the environment from deadly to tolerable in one long, smooth gradient. By the time you reach roughly 50 to 60 kilometers above the surface, a region that floats well above the worst the planet has to offer, everything changes. The pressure has fallen so much that it lands almost perfectly in the Earth-like range. not close, not sort of. Almost precisely the pressure you would feel strolling around a coastal city on a warm afternoon. It is an astonishing coincidence, a thick, intimidating atmosphere that, at a certain height, becomes the ideal environment for the human body without needing pressurization suits, airlocks, or life support tanks that make you feel like you are walking around inside a science museum exhibit. This is no small detail. Humans are not built for low pressure. At extremely low atmospheric density, like on Mars, our bodies behave in unsettling ways. Moisture evaporates faster. Breathing becomes a performance art piece in which oxygen is rarely invited. Even inside pressurized structures, the constant battle against the near vacuum outside creates engineering challenges that do not take weekends off. Mars's atmosphere is so thin that it barely whispers across the surface. Living there is essentially living inside a very large, very dusty vacuum cleaner, one that has no intention of letting your lungs enjoy a normal day. Venus's upper atmosphere, on the other hand, sits at the opposite end of the comfort spectrum. It is astonishingly supportive, the atmospheric equivalent of a firm but friendly handshake. Your body could stand in that pressure without complaint. Your lungs would not try to stage a dramatic exit. Your blood would remain exactly where it belongs, instead of trying to boil away under reduced pressure. It is one of the rare cosmic environments that does not require humans to fight physics just to stay alive. What makes this even more surprising is that Venus reaches this sweet spot without becoming too thin or too chaotic. The pressure remains consistent within its altitude band, forming a region that behaves almost like a natural air cushion. It is thick enough to support floating structures, should we ever build them, yet gentle enough that human physiology can coexist with it. This is the kind of environment that engineers dream of when designing habitats, a pressure range where materials do not struggle against constant stress, where structural design becomes simpler rather than impossibly complicated. The difference between Venus's upper atmosphere and Mars's surface is enormous. On Mars, explorers would need habitations that resemble pressure chambers, with walls designed to withstand the strain between the low external pressure and the human-safe environment inside. Every air leak becomes an emergency, every crack a potential life-threatening failure. The atmosphere there feels less like a partner and more like an adversary that demands constant vigilance. In contrast, Venus's upper atmosphere offers a kind of cooperative balance. Instead of trying to implode your habitat, it gently supports it, reducing stress on materials and reducing the intensity of engineering hurdles. The fascinating part is how naturally the pressure gradient forms. Venus's thick atmosphere compresses itself at the bottom, building an intense base layer. But as altitude increases, the immense weight disperses. The gas expands, and the pressure falls into perfect alignment with human needs. It is not an engineered system or a manipulated environment. It is simply how the physics of Venus plays out. It feels like a cosmic coincidence, a quiet gift from a planet better known for its volcanic temper. For colonization planners, this pressure advantage becomes a subtle but powerful reason to reconsider Venus. It opens the possibility of habitats that are not constantly at war with their surroundings. It allows for normal breathing pressures, simpler life support systems, and structures that do not need to withstand the vacuum of space or the crushing force of deep-sea equivalents. It creates a future where floating stations could drift peacefully in a pressure range humans instinctively recognize as safe. In a solar system filled with extremes, Venus's upper atmosphere stands out as one of the few places where pressure feels familiar. It is a quiet, stable zone tucked inside a world that, at first glance, looks entirely hostile. This contradiction is what makes Venus so intriguing. Beneath the terrifying surface conditions lies a region of gentle balance, a natural sanctuary hidden above the chaos, waiting to be understood. If there is one concept that makes Venus feel less like a nightmare world and more like the setup for a beautifully strange science fiction film, it is the idea of floating cloud cities drifting high above its hostile surface. It sounds outrageous the first time you hear it, like someone took the phrase "head in the clouds" a little too literally. But the physics behind it are wonderfully straightforward. Venus's upper atmosphere has a secret quirk, a kind of cosmic loophole that makes the entire idea not only plausible, but surprisingly elegant. It turns out that the very air humans breathe, good old nitrogen mixed with oxygen, the same stuff swirling around you right now, acts as a lifting gas in Venus's atmosphere. Not hydrogen, not helium, not something exotic that wants to explode at the slightest provocation, just plain breathable air. To understand why this matters, imagine taking a balloon on Earth and filling it with regular air. Nothing happens. The balloon falls because it weighs the same as the atmosphere around it. But fill that balloon with helium, and it rises because helium is lighter. Venus flips that entire logic inside out. Its atmosphere is dominated by carbon dioxide, a heavier gas than Earth's air. So if you were to fill a balloon, or better yet, an entire habitat, with breathable air, the whole structure would float. No magic, no complicated systems, just basic buoyancy doing its thing. The air we need to live becomes the same air that holds the habitat aloft. This creates one of the most visually captivating colonization concepts humanity has ever entertained. Giant aerostat cities drifting in the golden haze, gliding above a landscape too dangerous to touch, but too fascinating to ignore. Picture the silhouette of a floating habitat, perhaps as wide as a sports stadium, suspended inside a massive balloon-like hull. Below it stretches a world shimmering with heat and mystery. And around it lies an atmosphere thick enough to cradle human structures like a natural ocean of gas. Instead of walking on alien soil, settlers would live in the skies, an entire civilization built on the gentle balance between density and lift. This idea feels futuristic, but the underlying principles are ancient. Humans have relied on buoyancy for centuries, from hot air balloons to blimps to airships carrying cargo across continents. Venus simply offers far more help than Earth ever has. A structure filled with breathable air would experience lift equal to a balloon on Earth filled with helium, except without needing helium at all. Helium is rare and expensive, like the universe's version of luxury perfume. Oxygen and nitrogen, by comparison, are cheap, abundant, and essential. colonists would have to produce breathable air anyway. They might as well use it to hold up their homes while they are at it. These habitats would not be delicate bags wobbling in the sky. The designs imagined by scientists resemble sturdy, rigid structures with large internal volumes and segmented compartments. Picture a floating city with transparent sections, green spaces, solar arrays, laboratories, and living quarters, all suspended in an atmosphere that supports its weight by sheer chemistry. Life would not be cramped. The size of the structures could be enormous. The bigger the habitat, the more stable it becomes, since large aerostats resist sudden movements and can glide steadily with the winds. Some people imagine these floating cities slowly drifting around the planet like airborne cruise liners, following jet streams that circle Venus in a matter of days. Others picture anchored facilities maintained at fixed altitudes using tethers or controlled buoyancy systems. In every version, the environment around the habitat plays a crucial role. The sunlight is plentiful and diffused. The temperature is mild. The pressure is hospitable. Even the winds, though powerful, are predictable, more like steady rivers than chaotic storms. Colonies could tap into these winds for travel, energy, or climate control. Life in these cloud cities would feel less like an off-world bunker and more like living aboard a floating resort with endless sky beneath your feet. Living above Venus also introduces a strange emotional element that most space concepts lack. Instead of viewing barren terrain outside your window, you would see a world covered in swirling clouds and glowing horizons. Sunrises would spill through layers of haze, painting the sky in gold and amber tones. Nights would be veiled and otherworldly, filled with patterns of reflected sunlight dancing across the cloud tops far below. A floating city here would not just be shelter, it would be an experience. Every moment would remind settlers that they are suspended above a world that is majestic, mysterious, and fundamentally unreachable. The design of these habitats would rely on materials resistant to the mild acidity of the upper atmosphere, an issue that requires clever engineering but not insurmountable breakthroughs. The acidity in this region is diluted, more akin to dealing with persistent corrosion than with immediate destruction. With coatings and composites tailored to resist chemical wear, the structures could thrive long-term. Engineers already design equipment for environments filled with salt spray, volcanic gases, and chemical exposure. Building for Venus's upper atmosphere is simply another specialized challenge on that spectrum. What makes the floating city concept so compelling is how natural it feels once you understand Venus's atmospheric chemistry. You do not need to terraform the planet. You do not need to dig underground. You do not need to fight constant pressure differentials. You simply rise to the altitude where the world itself becomes gentle. In a solar system full of hostile landscapes, Venus offers something almost poetic, a reminder that sometimes the safest place to build a home is not on the ground, but in the sky. If space were a neighborhood, radiation would be the loud, uninvited guest who keeps trying to kick down your door. It is everywhere, pouring out from the sun, zipping across the galaxy, and drifting like invisible static that wants nothing more than to rearrange your DNA into modern art. Any planet hoping to host humans has to deal with this relentless cosmic bombardment. And this is where Venus quietly reveals one of its most extraordinary advantages. Venus's atmosphere is not just thick, it is astonishingly deep, dense, and protective. It is the planetary version of an armored shield, one that wraps the entire world in a cocoon so effective that cosmic rays barely make it past the outer layers. You can think of Venus's atmosphere as a fortress of gas, layered and massive, with each section absorbing or scattering radiation that would otherwise pummel anything unlucky enough to stand underneath it. The sheer bulk of this atmosphere, tens of kilometers of concentrated carbon dioxide in clouds, creates a natural barrier so strong that the surface receives far less cosmic radiation than many places on Earth. That is an extraordinary statement when you consider how violent the lower atmosphere is in every other sense. The same properties that trap heat so aggressively also block dangerous radiation with relentless efficiency. It is the ultimate example of a planetary system that is terrifyingly dangerous in one way, yet unexpectedly generous in another. But the real magic happens not at the surface, where temperatures behave like an ongoing meltdown, but in the upper atmosphere, the region where floating habitats would reside. Up here, the atmosphere is still enormously protective, but without the crushing pressure or heat that define the world below. Floating at 50 kilometers above Venus places you inside a protective shell equivalent to living beneath an enormous blanket of gas thick enough to intercept high-energy particles long before they can become a threat. A habitat here would benefit from radiation levels that are not just manageable. They are closer to Earth-like than anything Mars could ever offer. Mars, on the other hand, feels like it missed memo after memo when it comes to atmospheric design. Its atmosphere is so thin that it barely qualifies as a suggestion. One gust of solar wind, and the place might as well be wearing a sign that says, "Bring your own shielding." Mars has only the faintest wisp of atmospheric protection, so thin that cosmic radiation routinely reaches the surface with very little resistance. When you walk on Mars, you are essentially standing outside in a cosmic storm, wearing little more than a glorified bubble. The radiation exposure for long-term settlers would be significant enough to keep doctors nervous for decades. The contrast is so dramatic that it borders on theatrical. Venus surrounds itself with an immense atmospheric fortress. Mars strolls around in the cosmic equivalent of a paper jacket. Floating above Venus offers protection that is passive and constant, while living on Mars demands layers of technological infrastructure just to keep the radiation dose at a tolerable level. Structures on Mars would need thick walls, heavily shielded habitats, and underground chambers to avoid a slow, steady accumulation of radiation equivalent to spending your life inside an enthusiastic X-ray machine. This difference shapes everything, from long-term settlement planning to daily human comfort. On Venus, colonists drifting in the habitable cloud layer would not need to hide indoors like moles. They could enjoy windows, views, sunlight diffused through atmospheric filters, and a sense of openness that is rare in extraterrestrial environments. The atmosphere does the shielding for you. It is like living under a permanent umbrella that blocks cosmic rays instead of rain. Mars settlers, meanwhile, would face a lifestyle defined by radiation protocols. Outdoor time would be limited. Habitats would resemble sealed bunkers rather than homes. Every structure would need shielding built in, increasing weight, complexity, and energy demands. Even agriculture would need protection. Martian farms might have to be buried or shielded, turning the simple act of growing food into a high-maintenance engineering project. The protective value of Venus's atmosphere becomes even more remarkable when you consider the dynamics of solar storms. When the sun occasionally throws tantrums and unleashes bursts of energetic particles, planets with weak atmospheres and weak magnetic fields get blasted. Mars is one of them. Venus, lacking a global magnetic field but possessing an atmosphere thick enough to challenge even solar storms, responds differently. Its upper layers absorb and disperse much of the burst, turning what would be a hazardous event on Mars into a muted disturbance high above the level where habitats would float. This resilience transforms Venus's upper atmosphere into one of the safest radiation environments beyond Earth. It is a place where cosmic rays are deflected long before they reach settlement altitude. Colonists would not need to design their entire lifestyle around minimizing exposure. They could focus on exploration, research, and daily life without feeling like they are living in a world that constantly demands caution. There is something poetic about the idea. While Venus roars with heat and pressure below, its skies provide sanctuary. Radiation, one of the biggest obstacles to human expansion beyond Earth, becomes less intimidating here, simply because of the planet's overwhelming atmospheric mass. It is a reminder that even the harshest worlds can hold unexpected gifts, and that sometimes the most hostile planets hide surprising layers of safety just above the chaos. Venus's upper atmosphere, in its strange golden light, offers a refuge from cosmic radiation that no Martian dome can match. It protects, it shelters, and it invites us to imagine a future where humans drift in the skies of a planet that has always been misunderstood. Mars has a way of advertising itself as a quiet, lonely desert, but that serene image is about as accurate as calling a tornado a light breeze with ambition. If humans ever set foot on the red planet and tried to make themselves at home, they would discover that Mars has a collection of environmental quirks that range from mildly inconvenient to outright hostile. And unlike Venus, whose upper atmosphere behaves like a steady, predictable ocean, Mars delivers its challenges in the form of dust, storms, and terrain that seems almost designed to undermine enthusiasm. Let's begin with the famous Martian dust storms, those sprawling, planet-spanning spectacles that are far more dramatic than anything Hollywood could stage. These storms are not the roaring windstorms of Earth. Mars's atmosphere is so thin that even in the most intense tempest, the wind would feel like someone gently nudging you with a pillow. The real problem is the dust itself. Fine, abrasive, and capable of getting absolutely everywhere with the determination of a glitter spill at a preschool craft table. The dust is so tiny that it floats easily, clings magnetically to equipment and infiltrates mechanisms in ways that make engineers wake up at night wondering if they angered the cosmic gods. For humans, this dust is not just messy, but dangerous. Martian particles are filled with chemicals that break apart under ultraviolet radiation, forming reactive compounds that aren't friendly to lungs, skin, or electronics. Any habitat on Mars would need an airlock system designed like a car wash for astronauts, scrubbing particles off every suit and tool before letting them inside. Persistent exposure could damage equipment, degrade seals, and wear down surfaces with microscopic abrasion. Even solar panels, the lifeblood of Martian energy, would become ineffective if buried in fine dust, turning power generation into a constant cleaning challenge. Imagine living somewhere you have to sweep the roof every day just to keep the lights on. Then there is the regolith, the soil that covers almost every inch of Mars. At first glance, it looks harmless, like simple red sand. But this soil contains compounds formed under harsh radiation, including perchlorets, which are toxic to humans and can disrupt thyroid function. Working or farming with Martian soil would not be a matter of picking up a shovel and planting a seed. It would require processing, filtering, and detoxifying, turning agriculture into a chemistry problem rather than a gardening activity. Every interaction with the ground becomes a controlled procedure, making daily life feel more like maintaining a laboratory than living on a frontier. Mars's low atmospheric density adds a whole additional layer of difficulty. With barely any air to slow down spacecraft, landing becomes a high-stakes exercise in precision. Parachutes barely work, and rockets must compensate for nearly everything. Once humans are on the ground, the thin atmosphere fails to buffer temperature swings or hold heat. Nights plummet into severe cold, with temperatures dropping faster than an unplugged freezer. Even during the day, standing outside a habitat means being exposed to an environment that does not feel like air, so much as it feels like standing inside a half-forgotten attic, dry, nearly empty, and utterly incapable of supporting something as simple as a breeze. Sound travels poorly, heat escapes quickly, and maintaining pressure inside any structure requires constant reinforcement against a world that is always trying to equalize the difference. Now contrast all of this with Venus's upper atmosphere, a place that, despite being perched above a planet that could melt metal, behaves with a surprising amount of consistency. Instead of wild temperature drops or sudden exposure risks, the upper atmosphere offers a stable envelope with conditions that change gracefully rather than violently. Winds circle the planet in a uniform pattern, creating steady flow rather than unpredictable turbulence. These winds are strong but smooth, more like a reliable conveyor belt than a chaotic storm system. A floating habitat would drift along these currents, experiencing movement that is rhythmic rather than jarring. In the Venusian upper atmosphere, dust is non-existent. There is no soil to kick up, no abrasive particles to clog machinery, no toxic grit coating every surface. There are no sandstorms to bury solar panels or storms strong enough to rearrange landscapes. Instead, habitats float in a region dominated by gas rather than grit. Maintenance shifts from sweeping dust out of filters to simply monitoring aerostat materials for gradual wear. An entirely different set of engineering challenges, but ones that are not constantly escalating in drama. Most importantly, the upper atmosphere of Venus behaves predictably. Pressure, temperature, and wind patterns follow stable cycles. Storms do not surge unexpectedly. There are no planet-wide dust events that turn the sky opaque for months. This consistency creates an environment where daily operations can be planned with confidence. A floating colony might drift, but it would drift in a world that honors rhythm and repetition rather than upheaval. Mars demands perpetual vigilance, dust management, soil detoxification, constant maintenance of pressure systems, and careful planning around storms that can darken the entire planet for weeks. Venus's upper atmosphere asks something different: respect, engineering finesse, and caution regarding acidity, but not the non-stop crisis response that Mars seems determined to require. This comparison reveals a hidden truth. Danger does not always come from flames or heat. Sometimes it comes from quiet forces, dust, thin air, and chemical landmines scattered across a barren surface. Mars challenges human survival through subtle hostility. Venus challenges it through dramatic extremes, but only below. High above the surface, in that golden band of stability, Venus offers a kind of calm that Mars's rugged landscape simply cannot. When people imagine harvesting resources on another world, they often picture astronauts chipping away at Martian rocks like miners in a silent red frontier. The vision is dusty, rugged, and very physical. Mars encourages that mental image because its resources are locked in ice, soil, and stone, materials that require digging, drilling, melting, grinding, and a whole lot of power. Venus, by contrast, invites a completely different picture. There are no icy caverns, no boulders waiting to be cracked open, no underground pockets of water waiting to be melted. If Mars is the cosmic quarry, Venus is the cosmic chemical factory, one that floats, churns, and hums with atmospheric ingredients that humans could tap directly from the air. This difference rewrites the very idea of extraterrestrial industry. Instead of mining pits, Venus's future might look like networks of floating refineries drifting gently in the upper atmosphere, drawing raw materials not from solid ground, but from the thick stew of gases that surrounds them. Everything is already mixed, dissolved, or suspended, ready to be separated and concentrated. It is like walking into a restaurant where the ingredients are already chopped and simmering. You just need the right tools to capture and process them. The most abundant and immediately useful resource in Venus's atmosphere is carbon dioxide. This might sound unhelpful at first. On Earth, carbon dioxide is the gas we spend our lives trying to reduce. But in a colonization scenario, carbon is a treasure. Carbon is the backbone of plastics, polymers, fuels, and countless organic compounds. With carbon dioxide as the feedstock, floating habitats could synthesize everything from carbon-based building materials to breathable oxygen. Chemical pathways like the Sabatier reaction or more advanced catalytic systems could turn carbon dioxide into methane, oxygen, and complex hydrocarbons. It is as if Venus is offering an endless supply of raw carbon, waiting to be transformed into the essentials of human industry. Then there is sulfur. Venus's atmosphere is rich in sulfur-containing compounds that drift through the cloud layers like restless chemical ghosts. Sulfur dioxide and sulfuric acid aerosols may sound like a chemist's nightmare, but sulfur is a profoundly useful element. It can be refined into sulfuric acid for industrial processes used to make batteries, incorporated into fertilizers, or converted into elemental sulfur for manufacturing. Sulfuric acid is one of the most important chemicals in Earth's industrial civilization, an essential ingredient in everything from refining metals to producing detergents. Venus provides it in such abundance that floating facilities could extract it continuously, turning a planetary hazard into a lifeline. These chemical resources contrast sharply with the resource palette Mars offers. Mars is the planet of solids, ice embedded in rock, minerals containing iron, magnesium, and aluminum, and dust that holds trace amounts of useful elements, if you can get them out. Extracting resources on Mars is a bit like harvesting almonds. There is a valuable kernel inside, but you have to crack open a very tough shell first, then clean it, then process it. Water ice might be the easiest resource to obtain, but even that requires locating deposits, drilling into them, heating them, and capturing the vapor. Every step demands energy, equipment, and constant maintenance. On Venus, by contrast, the raw materials float around you in vast, never-ending supply. You do not dig. You do not drill. You simply siphon, separate, and refine. This difference in resource form, gaseous on Venus, solid on Mars, changes every aspect of colony design. Mining equipment for Mars would need to withstand dust abrasion, mechanical wear, extreme cold, and pressure differences. Refineries on Venus would operate in a stable pressure environment with predictable temperature conditions and a constant supply of feedstock drifting right past their intake vents. Instead of towering excavators and robotic drills, Venus's industry might resemble an airborne network of chemical processors, each quietly extracting carbon, sulfur, oxygen, and trace materials from an atmosphere that never runs dry. Even power production ties into this resource dynamic. On Mars, energy must be stored for dust storms or generated through nuclear systems to compensate for the weak sunlight. On Venus, sunlight pours into the upper atmosphere with an intensity Earth can only envy. Solar panels, perched safely above the clouds, could power electrochemical processes continuously. Electricity becomes the engine for extracting materials, splitting molecules, and forming compounds that serve as the building blocks for everything from plastics to fuels. And then there is the subtle advantage Venus offers: scalability. If a floating settlement grows, it does not need to send teams farther afield to find new deposits. It simply expands its atmospheric intake. The supply of carbon dioxide and sulfur compounds is planetary in scope. Every region of the atmosphere offers the same bounty. A larger colony simply means a larger network of collectors. This creates a rare form of freedom in extraterrestrial industry, the ability to grow without needing to conquer more terrain. Mars, with its scattered ice pockets and mineral deposits, does not offer this convenience. Expansion means moving farther, digging deeper, investing in more infrastructure, and contending with increasingly challenging terrain. Mars will never run out of rock, but extracting useful materials in a cost-effective, colony-friendly way will always be a negotiation with the planet's stubborn surface. Venus reframes that conversation. Its resources flow, they swirl, they gather in clouds and currents. They invite extraction, not by force or excavation, but by chemistry and capture. The atmosphere becomes an industrial ocean, a place where supply does not diminish with use, and where the tools needed to harvest resources float effortlessly beside the habitats that depend on them. The planets offer two profoundly different visions of survival. Mars challenges humanity to become miners, drillers, and excavators in a landscape etched with ancient scars. Venus, from its lofty refuge in the clouds, asks us instead to become chemists, distillers, and harvesters of gases. Each world demands ingenuity, but one offers its resources in liquid softness, while the other hides them inside relentless stone. In this difference lies one of the most important questions about our future in space. What kind of industry do we want to build beyond Earth? A world of rocks or a world of clouds? Energy is the heartbeat of any settlement, and off-world colonies are no exception. Without a dependable source of power, even the most carefully engineered habitats become oversized survival tents waiting for the lights to go out. This is where Venus quietly steps onto the stage with an advantage so significant that it changes the entire tone of colonization planning. While Mars struggles to power itself like a phone running on low battery mode, Venus's upper atmosphere practically showers any floating settlement with sunlight so plentiful and consistent that solar panels would feel like they have won a cosmic lottery. Then, the first and most obvious factor is simple proximity. Venus sits closer to the sun than Earth does, bathing in sunlight that is nearly double the intensity found on our home planet. It is as if the sun shines with a little extra enthusiasm over Venus, delivering a brightness that makes solar panels hum with delight. Even before considering atmospheric conditions, the raw solar flux at Venus's orbit gives any energy system a huge head start. A solar panel floating above Venus would receive energy with the eagerness of a sunflower at peak bloom, capturing photons at a rate that would make engineers grin uncontrollably. But sunlight intensity is only part of the story. The real gift Venus offers is consistency. In the upper atmosphere, above the thickest cloud layers, the sunlight is steady and unobstructed, filtered only enough to spread gently rather than scorch. These high altitudes sit above most of the reflective cloud decks, meaning floating habitats can bask in near constant illumination. Nights still occur, But the day-night cycle at these heights is gentle, with sunrise and sunset painted in long, diffuse transitions rather than abrupt shifts into darkness. The length of a Venusian day might be enormous down below, but the winds at altitude move so swiftly around the planet that habitats complete a full circumnavigation in just a few days, ensuring regular daylight regardless of the planet's slow rotation. This is a key point that often gets missed. Floating habitats on Venus would move with the atmosphere itself, riding the global winds that sweep around the planet like conveyor belts. As a result, they would encounter changing horizons far more frequently than a stationary observer on the surface ever would. Instead of waiting for Venus's glacially slow surface rotation to bring back daylight, the habitat simply travels into sunlight again. Energy systems would not languish through eternal nights or struggle through periods of darkness that stretch for weeks. Light returns quickly, reliably, rhythmically, making energy production far easier to stabilize. Now contrast that with Mars, where solar power is a daily exercise in compromise. Mars is farther from the Sun, which means the sunlight it receives is weaker, dimmer, and less generous. Panels there must work harder to capture the same amount of energy, and even when sunlight does arrive, the Martian atmosphere cannot be trusted to leave it untouched. Dust hangs constantly in the air, muting the light and reducing efficiency even on clear days. The situation becomes truly painful during dust storms when Mars decides to wrap itself in a blanket of rust-colored haze that blocks sunlight for weeks or even months at a time. These storms do not behave according to polite schedules. They grow, merge, and swell without warning, expanding until they cover entire continents or, at their most dramatic, the whole planet. A settlement relying on solar energy during a global dust storm would find itself squinting into the murky orange gloom while its power supply quietly shrinks to a trickle. Cleaning solar panels on Mars becomes a daily chore, almost a ritual of survival. Dust settles like a fine powder determined to smother every reflective surface it finds. Without regular cleaning, using brushes, electrostatic systems, or sheer persistence, energy output declines fast. Even robotic missions have experienced this struggle, panels covered in dust slowly dimming until another mission-saving gust of wind arrives to sweep them off. Relying on that kind of luck in a human settlement is not exactly comforting. Venus's upper atmosphere, by comparison, offers a near dustless environment. There are no wind-blown particulates to smother solar arrays, no soil to cling to electronics, no gritty layers waiting to be scraped away. Solar panels would remain clean simply by existing, washed continually by the steady winds and the chemistry of the surrounding gases. Maintenance shifts from cleaning dust to simply checking for long-term corrosion. An engineering challenge, yes, but one measured in months and years rather than daily emergencies. The reliability of solar power in the Venusian sky opens creative possibilities for energy storage and distribution. Floating colonies could deploy enormous banks of lightweight panels along the tops of their structures, harvesting energy continuously as they glide through the upper atmosphere. power cables, capacitors, and battery systems could be integrated seamlessly without the constraint of constant cleaning or fluctuating supply. Energy-intensive systems, air processing, chemical extraction, manufacturing, could operate with a steady, predictable rhythm. Even large-scale projects like producing fuel or supporting greenhouses would benefit from the stable, generous sunlight. Mars, by contrast, often forces planners to think in terms of alternative or backup energy systems. Nuclear power becomes nearly mandatory, not because solar is impossible, but because solar is unreliable at the scale required for a thriving settlement. A Martian colony would live under the permanent question of whether its next storm will choke off power, and for how long. Venus flips that anxiety on its head. Its sky is harsh below, but generous above. Its atmosphere is a shield, but also a platform. And its sunlight, bright and dependable, becomes one of the strongest arguments for building a future among its golden clouds. While Mars makes solar panels struggle for every photon, Venus creates a kingdom of light, a place where energy flows as freely as the winds. Living above Venus sounds dreamy, literally floating in the sky like a drifting city from a futuristic novel. But turning that dream into something humans can actually inhabit comes with challenges that are neither gentle nor forgiving. Venus may offer pressure and temperature that feel surprisingly friendly in its upper atmosphere. But that does not mean it rolls out a red carpet for engineers. Instead, it presents a list of logistical hurdles that read like a cosmic engineering exam. Build habitats that never touch the ground, protect them from acidic droplets, anchor them in turbulent winds without letting them drift into danger, and make sure the entire structure stays buoyant at all times. In short, Venus asks not for strength, but for finesse. Colonizing Venus requires inventiveness, delicacy, and materials that behave like armor disguised as silk. The first and most obvious challenge is the simple fact that everything must float. There is no solid surface on Venus where you can set down a foundation, plant a flag, or casually unload construction equipment. The surface is too hot, too pressurized, and entirely off limits for anything resembling infrastructure. So the colony must exist fully aloft, permanently suspended in the temperate cloud layer, never descending into the furnace below. This requires habitats designed like giant aerostats, massive air-filled structures whose internal gas composition is carefully balanced to maintain lift. It is one thing to build a hot air balloon that floats for an afternoon. It is another to construct a floating city that has to remain stable for decades or centuries, all while carrying equipment, people, laboratories, agriculture modules, and everything else a settlement needs. Keeping these habitats afloat demands constant attention to buoyancy. The air inside must always remain lighter than the Venusian atmosphere surrounding it, which means systems must continuously monitor temperature, pressure, gas composition, and structural integrity. If a habitat cools too much, the lifting gas may compress. If it warms too much, expansion must be managed. Internal adjustments must be seamless and automated. Floating cities cannot afford wobbles, sudden altitude drops, or accidental drift into unsafe layers. A lapse in buoyancy on Venus is not a small inconvenience. It is a slow descent into impossible pressure and heat. Engineers must treat altitude stability like a sacred ritual. But buoyancy is only the beginning. Venus's atmosphere contains sulfuric acid droplets, tiny persistent particles that ride the winds like airborne thorns. While the concentration of acid in the habitable layer is far from instantly destructive, it is constant enough that materials must resist long-term exposure. Everything external must be designed to shrug off acidity the way umbrellas shrug off rain. Protective coatings would need to be developed not just for hulls and frameworks, but for solar arrays, windows, air intakes, external wiring, and even the surfaces used for communication and observation. These coatings cannot simply be thick armor. They must be lightweight, flexible, and repairable in the air. The challenge is finding that perfect trifecta of durability, featherweight construction, and longevity. Maintenance in this environment becomes a specialized art. Robots equipped with acid-resistant plating might crawl along the outer surfaces of habitats, inspecting seams, patching protective layers, and scanning for chemical wear. Engineers would design modular exterior components so that pieces could be swapped out without compromising buoyancy. Entire maintenance cycles would revolve around the slow but relentless nibbling of sulfuric acid, treating corrosion the same way sailors treat barnacles on ships, an ever-present annoyance that must be managed with discipline and cleverness. Then there are the winds. The upper atmosphere of Venus is more cooperative than its infamous surface storms, but it is far from still. Winds at altitude whip around the planet with incredible speed, carrying habitats along like passengers on a planetary jet stream. While these winds are smooth and predictable, they demand anchoring solutions that are as elegant as they are effective. There is no ground tether to rely on, no anchor point to bite into. Instead, floating cities must use dynamic positioning systems, thrusters, aerodynamic fins, or buoyancy adjustments to maintain a safe altitude and avoid drifting into layers where temperature or pressure becomes unsafe. These winds shape the rhythm of life. A habitat might glide around the planet every few days, experiencing sunrise and sunset, not because Venus rotates quickly, but because the winds carry it through different longitudes. This creates challenges in communication networks, which must be designed for moving nodes instead of stationary bases. Satellites, high-altitude relays, and floating communication hubs would form a constantly shifting web, one that adapts to the gentle drift of each city in the sky. Logistics for supplies, repairs, and expansion must also adapt to this floating lifestyle. Cargo ships arriving from Earth cannot simply land. They must either dock with the habitat mid-air or release payloads that aerobrake into the upper atmosphere and use controlled descent to meet the colony. The docking maneuvers would resemble airborne ballet, precision, timing, and choreography governed by wind patterns and aerodynamic forces. Every object introduced into the colony must be light enough to float or must be incorporated into the structure in ways that preserve overall buoyancy. There are no landfills, no storage basements, no underground tunnels. Waste must be processed chemically, compacted, or used as feedstock for new materials. Every gram matters. Despite all these challenges, something remarkable emerges from the engineering problem: a civilization that lives lightly. Floating cities on Venus cannot be heavy, rigid, or reliant on brute force construction. They must be thoughtful, streamlined, and respectful of the delicate balance that keeps them aloft. They would be cities designed with the grace of aircraft, the resilience of ships, and the precision of spacecraft, all blended into one. Venus does not make colonization easy. It demands creativity, discipline, and innovation in every bolt, polymer, and circuit. But in that challenge lies a unique form of beauty. A floating city on Venus is not just a structure. It is a living equilibrium, a technological lotus blooming in the clouds above a world that tries to forbid life everywhere but its skies. Life on another planet would not just be a matter of machinery and survival. It would reshape how humans think, feel, socialize, dream, and even define the concept of home. Two completely different colonization environments create two radically different versions of humanity. One drifting through the golden upper skies of Venus, surrounded by light and open horizons. The other living beneath the surface of Mars, or sealed inside rigid domes, wrapped in layers of protective walls. These are not just engineering choices. They are psychological landscapes, and each one molds the rhythm of daily life in profound, subtle ways. Imagine waking up in a floating Venusian habitat. Your morning commute might begin with sunlight pouring softly through wide windows, filtered through distant cloud layers that scatter the light into warm tones. The sky around you is immense, horizons stretching in every direction, shifting slowly as the winds carry the city along its planetary route. The structure beneath your feet feels airy and open, suspended not by stilts or foundations, but by the invisible buoyancy of the atmosphere. Even though you know intellectually that the surface below is deadly, the immediate environment feels expansive and almost serene. You live in the sky, not on an alien wasteland. There is a sense of elevation, literally and emotionally. Psychologically, this creates a sense of openness that most humans crave. People evolved under wide skies, with natural light shaping mood, sleep cycles, and mental stability. Floating habitats offer panoramic windows instead of bunker walls, sunlight instead of dim artificial bulbs, and visual continuity with the surrounding atmosphere. Even though the world outside is alien, it is not claustrophobic. You do not feel buried, sealed off, or entombed. The environment still feels like a place, not a shelter carved into an abyss. Daily life can include shared observation decks, conservatories filled with plants, and communal spaces that overlook the golden glow beyond. Humans can see distance, light, and movement, elements that the brain likes more than it realizes. Contrast this with Mars, where most long-term settlements would likely exist underground or within thick-walled domes made to withstand radiation and pressure differences. Life there would be safer beneath the surface, but psychologically narrower. Your windows, if you have any, reveal a color palette dominated by red dust, shadows, and landscapes that feel desolate and static. Many Martian habitats would be designed like submarines or burrowed stations, corridors, pressure doors, narrow walkways, and artificially lit rooms. Functional, yes. Comforting, not always. People can adapt to enclosed spaces, but long-term confinement has well-documented psychological consequences. Disrupted sleep, decreased attention, increased irritability, and the sense of being cut off from the outside world. On Venus, people would live inside structures that float with the winds, creating gentle movement that might feel like being aboard a ship or gliding aircraft. This constant motion introduces a kind of natural rhythm, a slow, calm drift that mirrors waves or breezes. While some may need time to adjust, many would find it soothing, a reminder that the environment is dynamic and alive. Mars, by comparison, is often still, quiet, static. The silence outside the walls might feel peaceful at first, but over time it can slip into an unsettling emptiness. There is a psychological difference between living above a planet and living inside it, between floating and hiding. Social life would also diverge between the two worlds. A Venusian city, by its very design, encourages communal architecture. Large internal spaces would be easier to construct without the crushing pressure differences that Martian domes must endure. Shared parks, atriums, and gathering zones could be created within the aerostat structure, making the community feel like a single interconnected ecosystem. Movement between modules would be fluid, not slowed by pressure gates or safety doors. People could congregate in observation spaces, watching the clouds shift around them, forming a shared identity built on the habit of looking outward, not inward. Mars, however, naturally fragments its social architecture. Habitats need barriers, thick ones. Each dome or tunnel system becomes its own compartment, separated by airlocks, reinforced modules, and strict protocols. Group activities might require coordinating travel through pressurized passages. Large open communal areas would be limited, expensive, and carefully controlled. Even recreational activities would require artificial environments to simulate natural conditions. The result is a social framework where life is divided into segments: work module, living module, greenhouse module, with every step mediated by caution. The emotional effect of this difference is immense. On Venus, people may feel as though they are part of a sky-born community, sharing the same open environment and the same views. On Mars, people may feel more like residents of connected bunkers, a network of survival pods rather than a single unified city. Another factor is light. Venus's upper atmosphere provides continuous, filtered sunlight with softness that resembles perpetual dawn or dusk. This kind of diffuse light promotes calmness and regulates biological rhythms. Mars's surface, on the other hand, often dims under dust, leaving the world in muted tones even on clear days. Periods of prolonged darkness during dust storms could stress colonies, forcing strict reliance on artificial lighting, something known to disrupt circadian cycles and increase psychological strain. Finally, the symbolism of each environment shapes its culture. A city in the clouds has an inherently uplifting mythology. Humans rising above a hostile world, living lightly and drifting through the sky like technological birds. A Martian underground settlement feels more like a fortress, a carved-out refuge in a harsh, silent desert. One metaphor lifts, the other digs in. Neither reality is better in absolute terms, but each molds the human psyche differently. Venus offers openness, mobility, sunlight, and shared sky. Mars offers shelter, solidity, challenge, and the quiet determination of a frontier carved from rock. The question becomes not which planet is easier to live on technologically, but which kind of life humanity wants to build, one in the clouds or one beneath the stone. If humanity ever commits to building homes on another world, we are not just picking a location. We are choosing a long-term relationship with an alien environment that will test our patience, creativity, and survival instincts for generations. And while both Venus and Mars offer potential pathways into the future, each planet carries its own portfolio of hazards that do not simply disappear once the initial excitement fades. Instead, these risks simmer in the background like long-term complications in a cosmic marriage. You may not see them every day, but you ignore them at your own peril. Take Venus, for instance. In the upper atmosphere, conditions may be calm and stable, but the broader planetary system is anything but relaxed. Beneath the tranquil floating city zone lies a world simmering under relentless heat, wrapped in a greenhouse effect so intense it has become legendary. Venus did not just stumble into its current state. It spiraled into it through a runaway process where trapped heat pushed temperatures ever higher, evaporating early oceans and thickening the atmosphere until the planet effectively sealed itself inside a pressure cooker of cosmic proportions. The long-term concern is not that the upper atmosphere is unsafe now. It is that the system as a whole is unpredictable over geological timescales. The same mechanisms that trapped heat once could shift again if internal dynamics change, if volcanic outgassing increases, or if the delicate balance of atmospheric circulation evolves in ways we do not fully understand. Floating cities would depend on stable temperature and pressure bands. A shift in atmospheric layering, even a modest one, could force habitats to operate at different altitudes or stress buoyancy systems. Venus does not offer the luxury of a solid platform beneath a colony. Everything depends on the atmosphere remaining stratified in predictable layers. If the greenhouse engine powering Venus were to intensify, or if sulfur concentrations increased dramatically, the habitable layer could drift upward or downward, compressing the safe zone or introducing new hazards. Long-term settlers would need to become masters of atmospheric monitoring, developing predictive models that continuously track chemical composition, thermal gradients, and circulation patterns. Venus is majestic, but it is not passive. It demands respect, not just for what it is, but for what it might become. Then there are the sulfuric acid clouds. They may be diluted at higher altitudes, but they persist as a reminder that the planet's atmosphere is chemically aggressive. Over decades, even the best protective coatings could degrade, forcing constant maintenance and innovation in materials science. The acid droplets themselves are only one part of the challenge. The presence of reactive sulfur compounds throughout the cloud layers creates a chemical environment that is always nibbling, always testing, always probing at vulnerabilities. Floating habitats would not face catastrophic corrosion, but continuous erosion, a slow, persistent whisper that says, "You can stay, but you must work for it." Long-term survival would require an evolving understanding of materials, regular replacement cycles, and a robust system for regenerating or repairing structural components. Mars presents a completely different kind of risk, less dramatic at first glance, but far more insidious. Its problem is not runaway heat. It is the slow bleeding of its atmosphere into space. Mars lacks a global magnetic field, the protective bubble that shields Earth from solar wind stripping. Without that magnetic shield, the Martian atmosphere has been eroding for billions of years, thinning steadily under the pressure of solar particles. This is not a past tense problem. It is ongoing, continuous, and inevitable. If humanity builds a colony on Mars, it will be building it on a world that is slowly losing the very air it has left. This atmospheric thinning shapes the long-term habitability of the planet. Even if future colonists generate oxygen, create greenhouses, or pressurize their living spaces, the external environment will remain unstable. Radiation levels will stay high. Atmospheric density will remain dangerously low. And because Mars is unable to hold on to heat effectively, the planet is locked into dramatic temperature extremes that no colony can fully escape. Generations could pass, but the environment outside the domes would remain almost as hostile as it is today. Terraforming Mars has long been a dream in popular imagination, but without a magnetic field, any attempts to thicken the atmosphere would be temporary. Solar winds would strip gases away faster than humans could replenish them. The planet's long-term climate future is essentially static, locked into a cold, thin-aired existence that places a permanent ceiling on how Earth-like it can ever become. Long-term geological stability presents another layer of uncertainty. Mars's interior has cooled significantly. Without active tectonics or a molten core driving convection, the planet is geologically quiet, but perhaps too quiet. There are no plate movements to recycle nutrients or refresh the surface. A static world can be peaceful, but it can also be stagnant, offering no natural mechanism to support long-term environmental renewal. Mars may not undergo dramatic atmospheric shifts like Venus, but its lack of geological dynamism creates a long-term ecological ceiling that human ingenuity alone must overcome. Venus, by contrast, may still experience volcanic activity beneath its thick clouds. Some evidence hints at eruptions reshaping its surface in relatively recent times. A burst of volcanic emissions could alter atmospheric chemistry, injecting new sulfur or carbon compounds into circulation. For floating habitats, this means navigating a planet that occasionally shifts its tone, sometimes subtly, sometimes significantly. In essence, the risks of Venus are energetic, dynamic, and intertwined with a world still flexing its planetary muscles. The risks of Mars are quiet, gradual, and tied to a planet that has lost much of its internal drive. Venus may surprise us with sudden changes. Mars may challenge us with endless monotony and slow attrition. Neither world is perfect. Both require vigilance, adaptation, and deep scientific understanding. Venus challenges us with chemistry and motion. Mars challenges us with silence and decay. In choosing between them, humanity must decide not just which planet it can reach, but which set of long-term risks it is willing to embrace. When humans finally stand at the crossroads of interplanetary settlement, choosing between Mars and Venus will feel less like a scientific decision and more like a cosmic real estate dilemma. It is the ultimate apartment hunt gone galactic. Each world comes with a handful of features that sound wonderful on paper, and a corresponding list of problems so dramatic they could be characters in their own soap opera. Mars is the cold, dusty fixer-upper with great views and terrible insulation. Venus is the penthouse in the sky, provided you never step foot on the lobby level, because it is essentially a furnace with self-esteem issues. Neither world is simple, neither is safe, and neither will ever be a perfect second Earth. But in their flaws and contradictions, they offer humanity something priceless: choice, possibility, and the chance to rethink what habitable really means. Mars appeals to the explorer in us, the part that romanticizes deserts, mountains, and rugged landscapes. Its surface is accessible, tangible, and visually dramatic. You can point to a spot and say, "I live there." There is a kind of primal satisfaction in building domes and tunnels directly into Martian soil, carving out pockets of warmth beneath a frozen world. The red planet feels like the classic frontier, harsh but noble, dangerous but conquerable, empty yet willing to be shaped by patient hands. But that frontier charm has limits. Life on Mars would always carry the undertone of living inside something instead of within something. The ground is toxic. The air is thin, the cold is relentless, and the radiation outside remains a silent reminder that Mars is not gently holding humanity. It is tolerating us behind silicone, metal, and glass. Any settlement on Mars must fight to survive in an environment that gives nothing for free. Every breath, every crop, every sip of water is a victory against a planet that will never truly cooperate. Venus, on the other hand, surprises us with its dual personality. The surface is a catastrophe, the kind of landscape that laughs in the face of life, machinery, and optimism. But climb far above it, into the calm bands of the upper atmosphere, and the planet suddenly transforms. Gone is the crushing pressure. Gone is the blistering heat. What remains is a sky with temperatures humans can appreciate, pressure that feels familiar, and sunlight bright enough to power entire cities. Venus becomes a world of drifting habitats, of panoramic skies, and of living quite literally in the clouds. The romance of floating cities appeals to a different part of human imagination, the part that dreams of airships, skylines, and unsinkable sanctuaries carried by gentle winds. Yet living aloft is its own psychological puzzle. Settlers would exist in a delicate equilibrium, forever suspended above a hellish world they must never descend into. Everything must remain light, precise, and controlled. The sky is forgiving, but only if humans respect its boundaries. Stability, buoyancy, and corrosion resistance become constant companions, demanding vigilance but rewarding innovation. The colony floats, not anchored, not grounded, existing in a kind of atmospheric harmony that has no direct parallel anywhere on Earth. When we compare Venus and Mars side by side, the contrast becomes almost poetic. Mars offers solid ground but little else in its favor. Venus offers a perfect pressure zone but no usable ground at all. Mars challenges humans with emptiness. Venus challenges them with excess. Mars asks settlers to warm a cold world. Venus asks them to rise above a hot one. Mars is a lesson in endurance. Venus, a lesson in adaptability. In a way, they form a pair of cosmic opposites, each forcing humanity to confront a different aspect of its own resilience. Choosing between them becomes an exercise in self-definition. Do we value the familiar instincts of standing on land, even if the land tries to poison us? Or do we embrace the surreal beauty of living in floating cities, carried by a planetary breath that never stops moving? Mars might feel safer because its dangers are visible and predictable. A thin atmosphere, frigid temperatures, dust that creeps into everything. Venus's risks feel more dramatic and theatrical, but paradoxically, its upper atmosphere offers something Mars cannot, a place where the human body can exist without constantly fighting pressure differences or freezing to the bone. If these two planets were apartments, the real estate listing would look bizarre. Mars would advertise itself as quaint, rustic, needs extensive renovation, cold water only, sunlight available but dusty. Venus's listing would boast stunning penthouse views, natural climate control at altitude, elevator permanently out of service, lobby floor extremely discouraged. And somewhere between those descriptions, a future civilization would have to choose which set of problems it prefers dealing with. Perhaps the most surprising truth is that neither planet is objectively better. They are simply different solutions to the same question. Where can humanity stretch beyond Earth and still find a foothold or a floathold in the cosmos? Mars offers grit, persistence, and the allure of walking on alien soil. Venus offers elegance, light, and the dream of cities that drift like lanterns in the sky. In the end, choosing between Mars and Venus is not about picking the planet with fewer flaws. It is about deciding which planetary personality aligns with humanity's vision of the future. Do we embrace the ground beneath our feet, even if it is red and unforgiving? Or do we dare to live in the air, reclaiming the sky as our new frontier. Whichever path we choose, the universe has already given us the greatest gift of all: two wildly dysfunctional apartments in space, each with its own strange charm, each reminding us that life, no matter where we take it, is always a blend of struggle, wonder, and possibility.